Rutgers, and he'll tell us about recent developments in sphere packing that have connections to some of the stuff that has been going on in the electric sphere.
Yeah, so I've been asked to explain why modular forms came up to prove the sphere packing problem in dimensions 8 and 24. So I first think I should just get a little bit of background on the sphere packing problem. It is what it says. Mainly, it's a problem of putting as many small spheres as possible in a very, very asymptotically large aircraft hangar or something. So you have like a bunch of ball bearings in an aircraft hangar, and from experience, you can't fill up every nook and cranny if they're all equal sized. And what percentage of space can you fill up? So the problem is to prove the optimum value. Or another way to put it is, just in terms of the centers of the spheres, what's the densest configuration of points in Euclidean space? RD is a dimension, such that no two are distance less than 1 apart. So just to give a little bit of history on this problem, the case when the dimension is 3 was posed by Kepler. This was in 1611, the astronomer Kepler, and solved by Tom Hales. So there's 2 papers on this. One is 1998, the other is 2014, which has a computer check of the original proof. It's a long computational proof, but there are smaller dimensions. So if you look at d equals 1, then it's obvious the integers are the best way to do it. You take the integers, of course you could translate the integers a bit, and you could scale them depending on the radius of the sphere, but the radius of the sphere is independent of the problem. It's just a scaling. And then in dimension 2, well, so there's the famous sort of Eisenstein integers, which I haven't maybe drawn so well.
It's hard to see the dots from the back.
Yeah, so I didn't draw them correctly anyway, so it's... So some number theory here. Okay, and this was proven, well, I mean, I see 2 different camps of who to attribute it to, but I'll put 2 in here, at least for some political reasons. This is not considered a rigorous proof by everybody, and there's a proof by Toff in 1940. And now, so that's where things stood. So you see there was a lot of progress around this time. And then just in this year, so Marina Vyazovska put a stunning preprint online, solved the problem in dimension 8. Okay, so this was put on the archive on March 14th. And then a week later, quite a few other people, including myself and her, put a proof up for dimension 24. So that was a very busy week, and we certainly can't expect to have a new result every week like this. There's something very special about dimensions 8 and 24. So the best packing in dimension 8 is given by something called the D8 root lattice. So it was already thought that it was the best packing there. As in 24, there's a very good candidate called the Leech lattice. I think this plan is probably it's me now. So here it's the Leech lattice. So the lattice is a thing I'll talk about in a minute. These were already understood to give very good packings and almost certainly the best packings. For example, Henry Cohn and I had shown that the upper and lower bounds were within like 70, 80 digits of each other. With these examples, but then now there's a rigorous proof. So one thing that does jump out, depending on if you include this name or not, is every single name on this list, and a list of problems that is about a problem that's saying completely about discrete geometry is a number theorist. That's very striking. Now, partly that's because the solutions that have been found are very number theoretical, although not as much number theory here in terms of the solution. And there's a reason for that, is that when we've been able to solve these problems, it's because we humans tend to solve the problems that are easier. So why is it not known in dimension 4, for example? Well, the sphere packing problem is a lot easier in dimension 24 than it is in dimension 4. Why is that? Well, to prove a problem like this, you need to solve it. You need not just to have a good way to densely pack things together. You need to be actually to show you can't do any better no matter what you try. These packings are so good in dimensions 8 and 24 that humans were able to actually prove the bounds that match them. So it's really the packings that are the brilliant part of the story. And because there's something very special about dimensions 8 and 24, modular forms came up. So let me put something here. So I hope this is readable in the back, and I'm sure I'll get it. Okay, good. So I'll give two answers that complement each other. One is that the proof is based on harmonic analysis. And harmonic analysis is very connected with automorphic forms. But the other is that because of the special nature of the solutions, the whole box. And one day at Rutgers, David Vogan was giving a talk at an AMS meeting, and the battery ran out. So I ran out of the hall and I found out there's a box of batteries. So I put them in. They didn't work, and I realized that was the box for the used batteries. The second is that the EA, is great, and the leaf lattice are connected by theta functions. Modular forms. So perhaps I should say something about that. So let me define a lattice. I haven't done that yet. So I'm going to take the integral combinations of d vectors in Rd. We call this a lattice. That's simply that this means that v1 through vd is a basis. So this is a discrete set of points in d-dimensional space whose rank is the same as the dimension of the space. And just some other notation is that the volume, which really can be called covolume lattices, like this, which we denote by lambda. This is the absolute value of the determinant of this basis set. You put it, say, the columns into a matrix. So, of course, the determinant is could be plus or minus times the volume, so you put absolute values in. And then there's a notion of dual lattice. This is something that comes up already in algebraic number theory. So it's the vectors, there's inner products with every lattice vector. So just for clarity, I'm going to put too many adjectives in the sentence. You can get by with fewer. But this is a important notion. So let's say notion of even unimodular. And I'll write self-dual, even though that's actually something that follows from the other sentence. This means that, first of all, the lengths are always twice an integer. And the volume of the lattice covolume is 1. And also that the dual is itself. And so this is a bit redundant, but I just wanted to emphasize what the properties are. This is a very special class of lattices, even unimodular lattices. And they have theta functions. Any lattice has a theta function. These theta functions are special. So here's the definition. We sum over every lattice vector, and we take e to the 2 pi I times the norm squared of the vector times Now, the z here is in the complex upper half plane. And so this object, under the assumptions that it's even unimodular and self-dual, is actually a modular form. It's a modular form of weight d over 2 for SL2z. So this is the key connection already between lattices and modular forms. This function is just encoding how many vectors have a particular length. So, for example, if you do this for the you can define the theta function for any lattice. If you do it for the integers, you get Jacobi's classical theta function, which is a modular form of weight 1/2, but it's not for SL2z. It's for a different subgroup. In the special case that the lattice is unimodular and even, and I mean, normally what happens is that you get, on the other side, instead if you switch z to -1 over z, you get a sum involving the dual lattice. So if the lattice is self-dual, then you have a chance to be modular. These are very special conditions. These only exist when the dimension is divisible by 8. So here's some examples. So you could have an E8 lattice in R8. And of course, we have the Leech lattice in R24. And there are some other ones that occur, but these are very natural, and it's related to the fact that the space of modular forms is low dimension. So for example, if you plug in 8 here, we know there's only a one-dimensional space of modular forms of weight 4 for SL2Z. That's spanned by the Eisenstein series E4. So that tells you that theta of E8 is proportional. I mean, if you set up the constants correctly, it's equal to E4. And the theta function for the Leech lattice is a combination of, say, E12, the Eisenstein series E12, and then any other modular form there. So you could put, I don't know if you've seen the Ramanujan's delta form yet, but that's a good place to introduce it. This is a cusp form. So a lot of properties of lattices can be deduced from modular forms. For example, just because we know the space of modular forms is 1 or 2 dimensional means that we can completely determine how many vectors have length, say, 1,000, just from knowing the first few coefficients of this modular form. It completely pins all that down. This modularity, as you might guess, is a consequence of the Poisson summation formula. If you've seen that for the theta function for the integers. In that case, so maybe the most elementary example is this, which I'll write down in a second, is you plug the Gaussian into the Poisson summation formula, and then you resum it on the other side, and you see you get the theta function evaluated at a different point. So there's a version of Poisson summation over lattices. So I'm guessing many of you have seen Poisson sum over the integers. If you haven't, let's pretend lambda is the integers here for a second. So this is the best formula ever because it's going to tell you how to sum any sequence of numbers. Okay, so you know how to sum a geometric series. Now this formula will tell you to sum anything you ever want. It tells you that the sum on this side is equal to the sum over the dual lattice. So if you're over the integers, it's going to give you a different sum over the integers, which isn't going to make you very happy. Because now I've told you how to sum anything in terms of something just as hard, possibly. And here we have to normalize that by the volume of the lattice. And so you could take F to be a Schwartz function. I don't want to emphasize the analytic details of what class you can sum over, but this is a sort of an algebraic formula. And if you plug F as a Gaussian, you recover the theta function identity here. In fact, this theta function identity is equivalent. Well, it's almost equivalent to Poisson sum. I shouldn't say almost, but it's equivalent to a good chunk of it, to Poisson sum with modularity for radial functions, radially symmetric functions. Okay, that means that the value f is not sensitive to the actual vector, but just the norm of the vector. So it's a Schwartz function of the norm of the vector. Okay, so just to review, modular forms are connected to the lattices via the theta function, and the theta function is equivalent to the very powerful Poisson summation identity when restricted to radially symmetric functions. So now we've seen a touch of how harmonic analysis is entering the picture. But still, I mean, how is it going to enter into sphere packing and show bounds? So here is the key idea of the connection with that. And this goes back to Carl Ludwig Siegel, who looked at something slightly clumsy in retrospect. And then Cohn and Elkes looked at this around the turn of the century. And so let's make some hypotheses on F. So first of all, let's suppose that F of x is not positive for x, at least some number I'll call R1. So there's a good point here to say that if you have an even lattice here, by the way, so let's square it. If you look at the lattice lengths, we'll call them R1, R2, and so forth. Okay, so these will be square roots of even integers. And for example, for the E8 lattice, R1 is square root of 2. The Leech lattice is amazing. The Leech lattice is sort of the same size as the E8 lattice because the determinant is 1. But its first root is not at square root of 2. It's all the way at 2. It's square root of 4. That means you can stick twice as big a ball around every point in terms of the radius. You can double the radius as compared to E8, the Leech lattice. And that's why the packings are so amazingly good in 24 dimensions. Okay, so we're going to assume that the function f in Poisson sum is not positive outside the first vector. Okay, so in other words, that this means in particular f of lambda will be less than or equal to 0 unless lambda is 0. And let's now, on the other side, let's assume that f, the Fourier transform of f is positive, at least not negative. So Siegel only looked at functions of compact support, but Cohn and Elkes observed that you could allow the sign condition. So now let's take the Poisson summation formula and drop terms. This is a classic thing we do in analytic number theory. We have an identity, And we just throw away terms that we can't control necessarily, but at least we know their sign. And then we try and work with that. So, well, if we look over here, let's write the formula again. Poisson sum is the sum of values of f and then the values of f hat. On this side, well, the function is non-positive except at the 0 vector in the lattice. So I can bound this side by f of 0. Now, on this side here, I know that f hat is never negative. So I could say this whole right-hand side is greater than or equal to 0. If I do that, that's throwing out too much information. That's just telling me that f is positive at 0. So what I'll do instead is I'll just keep the one term for lambda equal to 0, and I can throw the other ones out because f hat is non-negative. So I get f hat of 0 over this volume, lambda. Another way to put it is that I have a lower bound for lambda. Okay, so that's provided that I can make such a function. Yeah?
What is the online for each of
Oh, it's, I wrote square root of 4. That's also 2.
Yeah, that's what I'm talking about. That's
Yeah.
what I'm saying.
Okay. Okay, so this is telling you that there's an upper bound on the volume of a lattice which has a vector of length r1. Density is number of points per space. So this is giving us an upper bound on density, just because this occurs in the denominator. So this gives a density upper bound. And upper bounds are what's hard to show. Well, this is the density upper bound for a lattice packing. Namely, a lattice packing here means that you, around every point in the lattice, you put a ball of radius r1 over 2. And then they'll never touch. So you might think, okay, well, if I want to show a particular lattice is the best possible lattice, I just have to have a function which has these sign properties and whose ratio of the values at 0 here. The Fourier transform matches the answer should be. And this is not easy to do. I'll show you how to do it for the integers in a second. That's pretty easy. But one thing is, you're probably saying, okay, well, I first was talking about the sphere packing problem. This is only for very regular packings that are centered around lattices. Maybe there's better packings that aren't centered on lattices. And in fact, we think that's true already, like in 9 or 10 dimensions. There are really good packings that are not centered on lattices that do at least as well, if not better, than the best lattice ones we know. So what do we do? Well, if it's not a lattice, you might consider a periodic packing. So periodic packing means that you have you center the balls on it. Well, periodic, it's what it sounds like. You have some big box, and you have some packing in that box, and you just repeat that box. And you can get the same formula, the same inequality there. Simply by translating the lattice. Okay, so in other words, the balls are centered on a finite union of translates of the lattice. If you want to put a plus v here on this side, it comes out with like an exponential phase on that side. That's just a consequence of the Fourier transform definition. If you add a bunch of them together in a certain way, you still have the same positivity, and you can repeat this argument. I don't want to write it down, but it's not really any harder. So that gives it bound for periodic packings, but you're like, well, okay, I mean, maybe there's some sphere packing that doesn't use a periodic packing that's better than any of the periodic packings we know. Well, this is, for tautological reasons, doesn't happen. The definition of packing is an asymptotic definition. So let's suppose we had an aperiodic packing that was better than any periodic packing. Well, that would mean if we took a really huge box, it would beat the density of any periodic packing. But then let's just repeat that box over and over again. Then we'd have a periodic packing with that density. So it's just part of the definition of limit that if you want to show sphere packing bounds, you just need to show them for periodic packings. The results about packing for the Leech lattice and E8 lattice show actually a uniqueness there's no periodic packing even ties to the Leech lattice or Yate lattice. So it's unique. It's not just the unique best lattice packing, it's unique best periodic packing. You could always take out one ball here and then take the limit, and then that would wash away. That we can't address. Okay, so the challenge is just right here, and then general packing down follows that definition. Challenge, we want to find f and f hat with the necessary properties. Okay, so that namely we need f. I'll draw a little picture of what they look like. Well, we need f to be non-negative. F hat is easy to draw, positive. F will be negative outside R1. So it's going to have some time, it'll probably be positive here. We don't really care what happens between here because there's no lattice vector. Just so you know, to show E8 and Leech lattice are optimal, what you need to show is that F hat and F both are the same at 0. So we can normalize that to be 1. So that's the ratio you have to show is 1 in that case. So it's an easy computation. So we'll start at 1. And here's R1 and R2 and so forth. So this will have to go down to R1. And this one will go down to R1. It could change sign in between, but after that it's got to be negative. But see, we threw out information in doing this. In analytic number theory, you throw out information. There's only one counterexample of what I'm saying that we know. When you throw out terms like this, you're going to lose information. You'll never get a sharp bound. Here we're asserting you get a sharp bound even though you threw out information. So how can that be? It must be the case that we actually didn't throw any information out. Namely, if everything is to be sharp, we don't want to prove something false. Right? So everything is to be sharp, we actually need all these things to be equal for this magic function that solves the sphere packing problem. Which means that f of lambda has to be 0 when lambda is a non-zero lattice vector. And similarly on this side. So this function has to vanish at R2, but it can't just vanish to first order because then we'll come up on the other side and it'll be positive. It's got to stay negative. So it's got to go back down and be negative, and it's never going to cross to be positive again because it can't be positive there. And this function, for the same reason, it's going to have to vanish here to not lose information. Which that true is incorrect. It's got to stay above the x-axis. And it will vanish at all these lattice lengths, but it will have double roots there. So there'll be double zeros in most of these places, except f of a single 0. So how do you construct functions like this? Well, I mean, it's very difficult generally to control a function in its Fourier transform. I promised you I'd show you how to do this for the integers. So here's the example for the integers. We take the function, which is 1 minus square root of x between minus 1 and 1. This is f. And then it's not hard to show that its Fourier transform is, I wouldn't remember this. So this is non-negative. It's clear the Fourier transform can't be negative because this little 10 function is a convolution of a characteristic function of the interval from -1/2 to 1/2 in itself. And convolution goes to multiplication when you take a Fourier transform. So something that is a convolution of itself will have a Fourier transform, which is a square, and so it can't be negative. And this vanishes at all the integers, like it's supposed to. And that's a perfectly good solution to the sphere packing problem in one dimension. Which of course is obvious to do, just the integers, but this is a proof of the approach. This approach probably works in 2 dimensions. It almost certainly does not work in other dimensions other than maybe 24. So that's luck. That's why what Tom Hales did is necessarily very hard if there's no proof like this there. Okay, so how are we going to control vanishing of both a function and its Fourier transform? Well, one way to do that is to try and diagonalize the Fourier transform. So the Fourier transform generally acts with order 4. I wrote f like this, sort of, even though it's a function RD, I'm tacitly making a radially symmetric function. There's no loss of generality in doing that at all. I don't want to waste time on that now because I don't have much more time. But if you look at, you could write f as f plus f minus, and then f hat is f plus minus f minus. Or here, these are Fourier eigenfunctions. So it's order 2 on radial functions, so we're just diagonalizing by sign. And then you have a similar picture for what f plus and f minus must look like. So f minus will vanish at the origin. So I didn't draw them to the right scale, but they basically look the same, except this one vanishes at the origin. They have single roots at R1, and they have double roots everywhere else. So we want to construct Fourier eigenfunctions with certain vanishing properties, and then hope that they have the right positivity properties. But this is already something that we need to do, is to control the vanishing. And this is the challenge. I mean, it could be that you construct these and it still fails because of the positivity. But Henry Cohn and I spent a lot of time, we were very fascinated with these functions, so we tried to compute them. So we developed a construction of these functions. The construction worked really nicely on the computer. Can't prove anything about it, basically. Couldn't prove it converged, but if one could prove it converged, then that would have solved the sphere packing problem. But from that, we were able to compute any statistic about it we wanted to very high precision through some effort. And so, so Cohn and I managed to calculate, not rigorously, but at least experimentally, a few features of these functions which are very striking. So for example, f plus of x near the origin has the following Taylor expansion. And then there's similar ones. This is for E8. I'm just going to write a sample of them down. There's many relations. This one is really striking. This is a bit artificial looking, but I wrote it just because I overheard one of the lectures this morning about a marker. And not one of these markers,